Hello everyone, this is the title of my presentation today, the DSM design of cold-form steel columns failing in flexural torsional modes at elevated temperatures, which work is co-authored by Antonio Bicelli, our master degree student at Federal University of Rio de Janeiro, Brazil, and the Portuguese team, Professors Dinar Camotim and Pedro Dinis from University of Lisbon. Very recently, Dinis and colleagues report the results of a numerical investigation of fixed and cold-form steel columns failing flexural torsional modes, covering a wide variety of cross-section shapes as shown in this plot. These results were compared to the current DSM column global strength curve, the solid black line shown here. And as illustrated in the second plot, this curve only provides accurate failure load prediction in the low to moderate slenderness, but underestimate for columns above this limit. Based on that, these authors also proposed a novel set of DSM design approach, denoted in this curve FNFT, which involves a set of strength curves dependent on the geometric parameter beta ft here and given by this equation. As one can see, this curve set predicts very well all the available failure loads. However, it remains to be assessed whether this strength curve set can also be adopted to elevate temperatures, namely those caused by fire condition, which is therefore the motivation of this work. So the objective of this work is to extend the scope of previous studies by presenting numerical results concerning columns with fixed end and support conditions, buckling and failing in flexural torsional modes, displaying various cross-section shapes, dimensions, and lengths, different yield stress in order to cover a wide critical slenderness range, and of course, elevate temperatures up to 800 degrees Celsius. So this is a quick view of the outline of my presentation today. First, I will address the column geometry selection procedure, then the main features of the ANSI shell finite element model used to perform nonlinear analysis for room and elevate temperatures is provided. After that, the results of the column's flexural torsional ultimate strength are presented in order to assess the merits of the DSM strength curves. Finally, the main conclusions of this work are provided. The column geometry selection was performed by means of a triannual buckling analysis strategy with the help of the GB2 code based on the generalized beam theory and satisfying the following requirement: fixed end columns, different cross-section shapes, elevate temperatures, and columns in pure buckling and post-buckling behavior in the sense that interaction is avoided. And this curve shown here provides the variation of the critical loading against the column length for a lip channel. And as one can see, this illustrates the select lengths and also the typical buckling mode shape. For elevated temperatures, the results are similar to these ones. The column post-buckling behavior and ultimate strength were performed with the help of the ANSYS code, involving column discretization with shell 181 element. All columns were modeled with an flexural torsion initial imperfection with a maximum magnitude of L over 1000. A two-step steady-state nonlinear analysis procedure was assumed where in the first step, a predefined uniform temperature is considered. Then, on the second step, the columns are actually compressed up to the failure, so one obtains the failure load at a constant temperature. Regarding the material modeling, the Eurocode 3 Part 1-2 model for cold form steel were considered. In order to validate the ANSI shelf-alignment model, one starts by reproducing the numerical simulations based on experimental tests by Badulaheva and Mahendra, as illustrated in this picture here at QUT Australia. This table summarizes the obtained results by these authors and in this work. As one can see, the mean values are relatively low, and which means that there is a good agreement between the obtained and the report values, which means that the shelf-aligned element model can be assumed to be validated. Now, in order to provide some DSM design considerations for fire conditions, the ultimate straight data results from a proposed parametric study involving 8,400 columns obtained from the combination of 210 geometries and lengths, 8 temperatures, and 5 yield stress with a FT slenderness range from 0.42 to 4.47, and also the 351 failure loads reports by Badulaheva and Mahendra correspond to 39 experimental and 312 numerical results dealing exclusively with lip channels are presented next. Following an approach already explored by other research, including ourselves, the original room temperature curves are then modified in order to account for the influence of the elevated temperature. This is done by including the reduction factors for the yield strength and also the Young modulus. These are the modified curves for elevated temperatures, and now adding the ultimate strength loads for temperatures up to 100 degrees Celsius. As one can see, the global estimates are safe and accurate only for lambda below 1.5, and on the other hand, the FT predictions are mostly safe and accurate for the whole slenderness range. Now, adding the results for higher temperatures, let's see, for 200 degrees Celsius, 300, 400, 500, 600, 700, and finally 800. One can see that both curves are clearly overestimated for this region here, which means that some modifications are necessary in order to improve the quality of the failure load predictions. So again, this is the first term of the strength curve, and the modification proposed consisted by adding the eta parameter in these two parts of the equation, here and here. This is the temperature-dependent reduction factor proposed. And now let's see the comparison of the ultimate strength curve, which is there is no modification for room and moderate temperatures, with the failure loads. So these are the results for room and 100 degrees Celsius. As expected, it's okay. Now, adding the results for the 200 degrees Celsius, one can see here the variation of the new curve proposed, the solid blue line here. Now moving to the results with 300 degrees Celsius, one can see the reduction in this strength curve, the variation of the strength curve. 400 degrees Celsius, similar conclusions. 500, now 600 degrees Celsius, 700, and finally 800 degrees Celsius. As one can see, there is this curve improves visibly the ultimate strength prediction quality for column displaying lambda below and equal to 1.5. Conclusions. This work was about an ongoing shell finite element numerical investigation on the post-buckling behavior, ultimate strength, and DSM design of cold-form steel columns failing in flexural torsion modes at elevated temperatures. On the basis of the parametric study carried out, it was possible to conclude that the available modified DSM design curve estimates for higher temperatures are only safe and accurate for lambda ft above 1.5. Outside this range, failure loads were clearly overestimated, meaning that some modification was required. That's what we did. The available DSM curves were modified by including the eta parameter, leading to a set of lowered strength curves for short columns ft lower and equal to 1.5. In spite of their simplicity, these equations curves were shown to improve visibly the quality of the failure load predictions. The next steps, we intend to do a experimental validation of this curve at the Federal University of Rio de Janeiro in Brazil. So thank you very much for your attention. This presentation is over.